All right, welcome back. Today, we're putting on our detective hats and diving deep into a classic case from one of the most legendary physics books out there, Irodov's Problems in General Physics. This one's a real brain teaser, folks. It involves two swimmers, a flowing river, and what seems like a totally impossible race. So you ready? Let's crack open the case file.
Okay, so here it is, the official problem statement, number 1.7. Let's break down the intel. We've got two swimmers. They both start at point A, and they both want to end up at point B, which is directly across the river. But they take completely different routes. Swimmer 1 goes straight across, no messing around. Swimmer 2 just swims straight out, gets carried downstream by the current, and then has to walk back to the finish line. And here's the kicker, the absolute key to this whole thing. They arrive at the exact same moment. Our mission? Figure out the walking speed that makes this paradox possible.
So, let that sink in for a second. One swimmer takes a diagonal path against the current. The other takes a swim-then-walk path. Two wildly different strategies, yet they tie. I mean, how does that even work? That's the mystery we're here to solve. We need to find that one single missing piece of the puzzle, the walking speed, that makes it all click into place.
All right, just like any good detective, the first thing we got to do is lay out all the facts. Let's get organized and see what we're really working with in this so-called river race. Okay, here's our evidence board. First, we've got the swimmer's speed. If the water were perfectly still, we'll call that V prime, and it's 2.5 kilometers per hour. We also know the river's current, V naught, is flowing at a steady 2.0 kilometers per hour. Then there's U, the walking velocity. That's our prime suspect, the big unknown. And finally, the width of the river. We don't actually know what it is, so let's just call it W for now. And as you're about to see, the fact that we don't know it might just be a clue in itself. All right, let's focus our investigation on swimmer number 1. This is the person who's all business, right? They're aiming for efficiency, taking the absolute straightest line from A to B.
But wait a minute, think about it. If you're in a moving current and you want to go in a perfectly straight line to the other side, you can't just point yourself at your destination, can you? If you did that, what would happen? The river's just going to sweep you downstream. So how do you fight that?
That's it. You've got to aim upstream. This is a perfect real-world example of vector addition. It's the same physics that pilots use to deal with crosswinds. The swimmer is pushing forward and sideways, while the river is just pushing sideways. By aiming just the right amount into the current, one part of their effort perfectly cancels out the river's push. The resultant velocity, the path they actually travel, is a perfectly straight line.
So what we've got here is a beautiful little right-angled triangle made of velocities. The swimmer's speed is the hypotenuse, the river's speed is one side, and their actual forward speed is the other. And you know what that means? Our old friend, the Pythagorean theorem, comes to the rescue. The resultant velocity, v1, is just the square root of the swimmer's speed squared minus the river speed squared. Plug in the numbers, crunch it out, and bam, 1.5 kilometers per hour. That's their actual effective speed toward point B.
Okay, so now that we know how fast they're actually moving across, we can figure out their total time. It's just distance over speed. The distance is the river's width, W, and their speed is 1.5. Let's write that down and stick it on our evidence board. T1 equals W over 1.5. Super important.
All right, one suspect down, one to go. Let's shift our focus now to swimmer number 2, the one who takes the scenic route.
Yeah, this person's trip is a bit more complicated. It's really a 3-act play. Act 1, swim straight for the opposite bank. Act 2, the river has its way and carries them downstream. Act 3, they get out and have to walk all the way back to the destination. Let's analyze each part.
So first up, the swim. Since they're aiming straight across, they get to use their full engine power, that full 2.5 kilometers per hour, to get over the width W. So their time in the water is just W divided by 2.5. And get this, their crossing speed is actually faster than swimmer 1's. Interesting, right?
But, of course, while they're making that fast dash across, the river isn't just sitting still. It's pushing them downstream the whole time. How far? Well, we just multiply the time they spent in the water by the river's speed. So that's W over 2.5 times 2.0, which works out to 0.8 times W. That's exactly how far off course they land.
And now our main suspect enters the scene, the walking speed U. The time it takes them to walk back is simply the distance they drifted, that 0.8 W, divided by their walking speed. This is the last leg of their journey. Okay, so to get the full picture for swimmer 2, we just bolt those two times together, right? The swim time plus the walk time. So their total time, T2, is W over 2.5 plus 0.8 W over U. And there we have it. We've got a complete timeline for our second person.
Okay, people, this is it. We've tailed both our swimmers. We've got their stories. Now it's time for that classic movie moment where all the pieces click into place.
So look at this. On one hand, we've got the time for swimmer 1, W divided by 1.5. Simple. On the other hand, the total time for swimmer 2, W over 2.5 plus 0.8 W over U. We've basically translated their entire journey, their whole story, into the language of math.
And now we pull out the single most important piece of evidence from the very beginning. Remember this line? Let's read it again. Both swimmers reach the destination simultaneously.
What does that mean for us? It means these two completely different-looking expressions are equal. They are the same. T1 equals T2. This, right here, this simple little equation is the key that's going to blow this whole case wide open.
All right, we've got them. The equation is set. Our unknown variable U has nowhere left to hide. It's time to do the final math and close this case.
So we set our two time expressions equal to each other, and then something almost magical happens. You see that W, the width of the river, the one thing we never actually knew? It's in every single part of the equation. Which means, poof, we can divide the whole thing by W, and it just cancels out. It's gone. It didn't even matter in the end. How cool is that? Now we're just left with a clean little algebra problem.
So we do a little bit of rearranging, move some terms around to get U by itself, and we find our answer. 3.0 kilometers per hour, and that's our culprit. That is the walking speed that makes everything work. Case closed. But you know, getting the right number is only half the fun. What's the real lesson here? What's the problem-solving technique we can take with us from this case?
This problem is just a perfect example of a super powerful strategy. First, you deconstruct it. You take a big, messy scenario and break it into smaller, manageable pieces. Then, you analyze each piece on its own. The journey of swimmer 1, the swim part for swimmer 2, the walk part. The real trick, the breakthrough, is finding that one linking variable. In this case, the fact that their times were equal. That's what lets you connect everything together and solve the whole puzzle.
And that, my friends, is how you crack a classic Irodov problem. But before you go, let me leave you with a little something to chew on. Go back and look at the math for swimmer 1, the one who went straight across. What would happen if their swimming speed was less than the river's current? Could they even make that direct crossing at all? The math holds a very interesting answer. Think about it, and we'll see you for the next case.